2.3e. Huzzah. This is new stuff. It is a lovely bridge in between KEQ and your diagrams, and it's going to bridge right into entropy and enthalpy. So go pick stuff up if you just came in. We're doing the lab tomorrow, after the quiz. We are not going to have a 2.5-hour long quiz. That's ridiculous. Well, yes, but if I say tomorrow and you're on a Tuesday, what do I mean? Okay.
Is this the review package for the
whole unit?
Okay, sweet.
Whole unit. Today is Tuesday. So I will see you on Thursday. I see you on Thursday, yes. It's okay, I'm barely functioning. I haven't had lunch, and I can tell because my brain is like even more like loosey-goosey than normal. It's kind of like, woo, what's happening? I don't know. Huh? Have to what? Dialed? Oh, but that's okay, because I'm just going to keep going. I'm just going to keep going. So, the value of KEQ, this is the new one you just picked up, 2.3e. 2.3e. Okay, open to your first page. KEQ. K, of course, stands for constant, and it is constant at constant temperature. Is there anything, thank you, Norman, that can change the KEQ value for a particular system? Well, let's go through this little summary table. And the first thing I'm going to get you to do is KC. We should really change this to KEQ. Okay, so that should be a KEQ. If I change the concentration of a reactant or product, that will cause a change in the position of the equilibrium, yes? That is called a, what do we call it when it changes position? We call that a shift. Okay. So if I change concentration, we will get a shift in the equilibrium. However, KEQ will not change. If I change the pressure, will the equilibrium position change? If I change pressure, will we get a shift? Yes. Shift. Yes. Only if gaseous and only if there's a different number of gas molecules on each side. However, KEQ does not change. And in fact, I'm going to focus in on all the things that don't change. Also, if we add a catalyst, you remember there's no shift, right? No shift. Okay, and so we have no change. Does it make sense that something that is called a constant will mostly not change? Okay, and that's why it is a constant. We can change the concentration and it stays constant. We change the pressure and it stays constant. We add a catalyst, it stays constant. If we add an inert gas, constant, no change. The only thing that will change a KEQ, and it will always change a KEQ, is the temperature. Temperature will not only cause a shift, but it will also cause the KEQ to change. Unless delta H is 0, you can just ignore that because that's never going to happen in Chem 12. Okay? So, only a temperature change only a temperature change will change the value of KEQ. I'm actually not going to go through this next chart right now. It's just sort of here as a summary. And I thought it would be nice to have both summary charts on the same page. But we're just going to skip past it now, and you can go back and review it when we're done the whole thing, okay? So, why does changing concentration not affect the KEQ? Well, in this part of the diagram here, we've got this equilibrium, PCl5 in equilibrium with PCl3 and Cl2. This here is our old equilibrium. Yes? And then we had our stress, which was, what was our stress? Yeah, we had an increase in the concentration of PCl5. Where does the concentration of PCl5 end up compared to its original concentration? It is higher, yes? So our new concentration of PCl5 is greater than our old concentration of PCl5. How about the concentration of PCl3? Is it higher or lower? The new concentration of PCl3 is bigger than the old concentration of PCl3. Can we say the same thing for the Cl2? Yes, we can. In fact, all the new concentrations are bigger than the old concentrations. So what that means is that in our original KEQ, we had certain values, and let's say that this was our old KEQ. In our new KEQ, I'm going to make my concentrations bigger by drawing them bigger. So I have P, and I'm going to make them narrow because otherwise I'm going to fall off the page. PCl3 is now bigger than it was before, yes? Concentration of Cl2 is bigger, and concentration of PCl5 is bigger. Is the ratio going to be bigger, smaller, or stay the same? The ratio is going to stay the same because both the numerator and the denominator got bigger. Therefore, KEQ stays the same because KEQ is that ratio. Is good? You are not actually going to have to be able to explain this. It's only to help you remember, right? But if you can just be like, okay, concentration, changing concentration does not change KEQ, that's all you really need to know, okay? Give you guys a minute to get that down. Now we are going to go on to looking at pressure. And when we're looking at pressure, what happens if we decrease the volume of a container? What happens to all the concentration? All the concentrations increase. And I wanted to bring that to your attention because there were a few people on the quiz who didn't change their concentrations when we had a change in volume, okay? So you can see they all go up, and then even though the SO2 now goes down and the O2 now goes down and the SO3 now goes up in the shifting process, where are all of these new concentrations? They're at equilibrium. What can you say about them relative to the original concentrations? They're all bigger than the original concentration. So the new concentrations are all bigger than original concentrations. So what does that tell us about our KEQ? KEQ stays the same for the same reasons as above. Now we come to temperature. Should we have a change in our KEQ? Yes, we should, because we know that temperature will change the KEQ. Let's look at why, but I'll let you finish writing this first. Okay. So why does changing the temperature change the value of KEQ? Well, let's look at what happens when our mixture was cooled. So we decreased the temperature, so that system shifted to the, if we decrease temperature, it shifted to the right to release heat to bring the temperature back up. Okay, so we made more NH3. So this is a bigger concentration, yes? What can we say about our H2? It's a smaller concentration of H2, and we also have a smaller concentration of N2. What that means is that this number on the top got bigger, and this number on the bottom got smaller. Now, if we have KEQ is equal to now a bigger number over a smaller number, what does big over small give us? Big. Yes? And it's going to be bigger than before. And it's going to depend on whether you're increasing temperature or decreasing temperature and where the heat term is and all those lovely things, yes? So what if we take a look at this example here? we have our heat term is over here. What is going to happen to the value of KEQ when temperature is increased? It's going to get bigger? Let's think it through, okay? If we increase the heat, which way does the equilibrium shift? Equilibrium shifts left. And if it shifts to the left, what's going to happen to the concentration of the products? When you go this way, are you using up product or are you making product? You're using up product, yes? And so what's going to happen to the concentration? If you're using it up, you're going to have less product, so this is going to go down, so it's going to get smaller, yes? What's going to happen to our reactant? We are making reactants. So that's going to, concentration of reactant is going to get bigger. And remember, KEQ, of course, is product over reactant. And we now have a smaller number over a bigger number. And if that's the case, what can you say about KEQ? KEQ has gotten smaller. Let's do the same thought process for the next one. What's going to happen to the value of KEQ if we decrease the temperature? Which way will the equilibrium shift? It will shift to the right. So the system shifts right. Why? To release heat, to replace the heat that was lost, so the temperature goes back up. Okay. So what's going to happen to the concentration of products if we're shifting to the right? It's going to get bigger, so it's going to get bigger. Concentration of reactants is going to get smaller. Therefore, our KEQ, which is products over reactants, is going to, the products got bigger, so I can have a bigger number over a smaller number. And that's going to give us KEQ out bigger. You do not need to write all of this out. If you're just like, okay, so what happens to KEQ if the temperature is increased? If you're like, increase it should be smaller. That's all you need to be able to do. You don't need to be able to walk me through all the steps. So, but if writing it out helps you, then please do so, okay? You guys are going to try the next two, all right? And then if you're successful with those, you can even try the two after that as well, okay? If you get stuck at all on one here. If you get stuck at all on this, like if this were a question where you didn't have the other ones before, always just write yourself a really simple little equation, yes, and you can say to yourself, well, I increased temperature, KEQ increased. Well, if KEQ increased, which way did we shift? We shifted right. And what that means is that where did our heat term have to be if an increase in temperature made us shift to the right? The heat term had to be here. So that's probably one of the easiest ways to deal with that, yeah? All right. Carrying on. What does the value, and I'm sorry that I'm rushing, but my last block we didn't get through everything, and so I promised them we'd record it, and you guys want to get through everything, so let's do it. We can do it. What does the value of KEQ tell us? Well, if we have a large KEQ, that means that the numerator must be large, that means the products must be large. Yes? And the reactants are going to be small. Vice versa. If we have a small KEQ, that means that the concentration of products is going to be small. Yeah? I always like to think of it in terms of products because they're on the top, it's easiest to think about. But you can also be like, okay, I've got something big on the bottom, that's going to make my overall number very small as well. Now, large, small, those are kind of wishy-washy terms. What is large, what is small, yes? For these ones? Probably not. No, they'll probably be in a multiple choice question, so you just have to pick the right one. That would be my guess anyway. I'll let you know if I make the test and it's different. Okay. Focus. Focus. If the KEQ is greater than 1, that's what we're going to call a large KEQ, because what that means is our denominator was bigger than our numerator. Okay? So if KEQ, oh, this pen's dead. If KEQ is greater than 1, that's what we call a large KEQ. That means that our product concentration is bigger, and the way that we all often express that is that we say that the products are favored. Yes? So when we say if products are greater than reactants, that means we say that the products are favored. You guys are chatty today. If the value of KEQ is less than 1, yeah, that means we have a small KEQ. And that means our denominator is the bigger one, so that means our reactants are bigger than the products, and that tells us that the reactants are quote unquote favored. That's the language that you need to get used to. Okay. Now we can go into a little more detail than that. We can say, okay, well, the larger the KEQ is, the bigger the quantity of the products, so the more the products are favored. So the larger the KEQ, the more the products are favored. The smaller the KEQ, the more the reactants are favored. Now, sometimes we're going to come across a case where KEQ is called very large. Very large. And if that is the case, what that means is that our concentration of products is going to be really, 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 really big, and reactants is going to essentially go to nothing. So you're going to take all your reactants and it's going to turn all into products. If you burn a candle, burning a candle, and you let it burn until the candle is all gone, it's all turned into CO2 and H2O, yes? That's what we call going to completion, okay? Is that a reversible process? No. So when you have a reaction that goes to completion, that is not a reversible reaction. It's just one way. And so your arrow will be a one-way arrow. If KEQ is very small, that means that the concentration of the reactants is really, 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 really big, and the concentration of products is really, really, really small. And in essence, it means that the reaction does not even occur. Yes? Imagine that I took some CO2 plus H2O. Can I get a candle? That can happen. CO2 and H2O, make candle. No, it does not happen, okay? So this is going to be a no, okay? Does not occur. Yes, and that's going to be if your KEQ is very, 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 very small. And this ties in really nicely with entropy and enthalpy, because if both entropy and enthalpy are pushing towards the products, the reaction is going to go to completion. If both entropy and enthalpy are pushing towards the reactants, that means that reaction is just going to stay as reactants and they'll never go to the products. You cannot make a candle out of carbon dioxide and water, okay? And if you have one of them pushing one way and one of them pushing the other, then you get an equilibrium, okay? If you have done the entropy and enthalpy tutorial number 2, and you just want to start working on things, you can start working on, you can do the exercises for 2.3E and 2.4F. However, if you're like entropy and enthalpy, what are you talking about? I did not do this. Then we're going to do it together, okay? Huh? Oh, F, that should be A. That's my brain. You remember I said my brain was going to do some weird things? That was one of them. You're like, whoa, where'd that come from? I don't know. All right. This is just free-form notes, okay? I'm not doing this in a tutorial. This is just free-form notes. Enthalpy. What's the symbol for enthalpy? H. And then if we have a change in enthalpy, change in enthalpy is delta H. Will these notes all be available for you? Yup. If you need to ever define enthalpy, our official definition is the heat content of the system. However, that's not a particularly useful definition. So it is useful to think of enthalpy and bearing in mind this is not the definition. And if you read Hebden, he'll be like, think of it this way, like all the same things. It was so funny because when we finally got Hebden as a textbook, I'm like, oh, this man just explains things just the way I do. Imagine that, all the chemistry teachers come up with the same ideas. Oh, because it's all the same stuff, right? This is not a definition, but it's a good way to think about it. It is useful to think of enthalpy as the potential energy contained in the chemical bonds. Okay, so if I say potential energy, you think enthalpy. What does nature love? I've got a second part to this question, just hold on. What does nature love? To be at high potential energy? Or low potential energy? So, here's my pen. It's at kind of a medium potential energy, yes? Can I make it higher? What do I have to do to make the potential energy and higher? I have to lift it up. Did that happen on its own? No. What did I have to do? I had to do some work, yes, to make it go up. Where does nature say, okay, pen, if you want to go all on your own, where's it go? Down. So nature loves a state of low potential energy. So for example, a ball will spontaneously, naturally roll down a hill. Okay, spontaneously means naturally, without us doing anything, the ball will spontaneously roll down the hill. We can make a ball roll up the hill. But that's a non-spontaneous process. It requires us to put some energy in. Okay, so whatever nature loves is what's going to happen spontaneously. Whatever nature doesn't love, that's what we have to put work into making it happen. Okay? Yes? the heat content of the system. But I don't want you thinking about it that way because that doesn't really mean a whole lot. You know what I mean? Think of it as the potential energy of the system, okay? Think of it that way, but if I actually ask you to define it, just spit out the heat content of a system. I feel as unhappy about that as I did in grade 12 when I was in your shoes, okay? Because physical chemistry is one of the hardest chemistries. People say organic chemistry is hard, that's because the organic chemists don't really take physical chemistry unless they're serious. Biologists, they're all like, oh, organic chemistry is so hard, ha ha. I'm like, no, it's not. Not compared to phys chem. Okay, going a little crazy now. So, late nature loves to be at low potential energy. And I'm gonna show you guys another way of saying low potential energy is to say minimum enthalpy. Does that make sense? Because low, actually I should even say lowest potential energy. Lowest is minimum, yes? And potential energy is the enthalpy, okay? So if we were to draw a potential energy diagram, which we could also call an enthalpy diagram, first of all, is the forward reaction endo or exo? Forward reaction is exothermic. And the reverse reaction is endothermic. Where on this diagram would nature prefer to be? Hold on. No, I don't want to hear reverse because reverse is a direction. Reverse encompasses this whole thing. Yes? Where does it want to be? Endothermic, that's the whole thing. It wants to be on the right side. Yes, it wants to be down here. Yes? So nature wants to be down here. At the lowest potential energy. What else could we call lowest potential energy? Minimum enthalpy. So if I said this to you based on enthalpy alone, are the products favored or are the reactants favored? So remember, our reactants are here, right? And our products are here. So nature wants to be here. Okay, we're always just going to talk about, even if we have a reversible reaction, we're always going to talk about the stuff over here as the reactants and the stuff over here as the products. So it wants to be at the products, yes? So based on enthalpy alone, the products are favored. Of course, if we do the reverse process, there's our products, there's our reactants. Where does nature want to be? Reactants. So this has the lowest potential energy. It has the minimum enthalpy. And therefore, in this case, we can say the minimum enthalpy favors the formation of what? Does nature want to be up here? Reactants. Because that's where nature wants to be. Nature wants to be at the lowest state. So minimum enthalpy is here, and that's our reactants. Okay? So we're going to do a little quick fire questions. Don't feel obliged to write these down. Like I said, this is going to be posted. So you can just chat with your partner about it. Which side, products or reactants, does minimum enthalpy favor? A. Heat plus A in equilibrium with B. What do you guys think? So if we were to draw a graph for this, what would it look like? It would be endothermic. So where do we want to be? Reactants. Excellent. Okay, what if we had C in equilibrium with D, and what if delta H was positive 30 kilojoules? Still reactants. Why? Where does that heat term go if it's positive? Goes in the reactants. Yes? So that's essentially the same question as the first one, yes? The only thing you have to remember is that if you have a positive value, that goes in the reactant. So I'm actually just going to highlight the sides that are favored here, yes? Do another one. E in equilibrium with F, and delta H is negative 10 kilojoules. Products, because where does our heat term go? On the right side, plus 10 kilojoules. And so that's going to look like exothermic. And so it wants to be where? On the product side. Okay, so this one's going to be reactants. This one's going to be products. And so let's highlight this here. There we go. What if we had G in equilibrium with H plus heat? Still our products, right? And quite frankly, I probably didn't need to do all of those, but I also want you to notice a trend here. In general, enthalpy always favors the side with the what? The heat term. Minimum enthalpy always favors the side with the heat term. In other words, the exothermic direction. And if enthalpy were the only factor in pushing reactions one way or the other, that would mean that exothermic reactions would always proceed, and you would never ever have an endothermic reaction, yes? Because enthalpy says no to endothermic, yes? But endothermic reactions do occur. So there needs to be another factor involved. And what is that factor called? The other factor is called entropy. And I'm sorry for its symbol, S, which makes no sense, but there we are. Hey, you do that. No. Didn't I just say it makes no sense? It makes no sense. Nope. No sense whatsoever. Huh? Because there's an H in enthalpy. I'm making that up. I don't know. Okay. Entropy is the randomness. You can make it S for randomness. I don't know. Of the system. Nature likes to go towards more randomness or less randomness. What do you think? More randomness. You guys have seen my desk, right? In the morning, this desk is always cleared off because I've got another teacher who's in here first thing in the morning. I make sure at the end of the day, this desk is clear. What does it look like now? It looks messy, and that's because spontaneously, there are papers all over. It's actually not as bad as it was earlier because I demonstrated in my previous class that if I wanted to make it less random, I would have to put in some work, yes, and go, oh, this long sheet doesn't belong with these quizzes, and oh, these are answer keys to the equilibrium review. Wouldn't that be nice if I put them over where they're supposed to be? Making things less random, organizing them takes work, okay? Nature spontaneously goes towards more randomness. So nature spontaneously tends towards, and we're not going to use the words more randomness, we're going to use the words maximum. Maximum what? Entropy. Okie dokie. Now, we're going to give ourselves a little scale here. We are going to go from the largest randomness to the smallest randomness. And this is because you need to be able to look at a reaction and tell which side is more random than the other side. Huh? And there's no 2.4a? It's because tutorial 2 is 2.4a. I just didn't have time to make it look nice and give it page numbers and stick it in the booklet because it's a PDF file and it did not agree with me. Yeah? Okay. Out of all the states of matter, what is the most random? Gas. Out of all of the states of matter, which is the least random? Solid. You have two states left, aqueous and liquid. Which one is more random? Liquid is less random because it is not a mixture. Aqueous is part of a mixture, and mixtures are by definition more random. If I have two things, two different things, that's more random than if I only have one type of thing. Okay? So, aqueous and liquid. Yeah, solid, the particles are not moving around much. They're like all organized. They're in little rows. You know what I mean? They're just, yep. Mixtures are more random than pure substances. We might just get through this. Let's see if we do. Which side does nature favor? The smallest randomness? The largest randomness? Nope. Yep. And let's do a couple of examples here. Okay. That's a solid. We have B, which is a aqueous. And we're going to say, we don't know what this arrow is doing. Yes, we're like, does it go forward? Does it go backwards? Is it equilibrium? We don't know. C, aqueous plus D, gas. What does nature like? C and D. Nature likes the products because maximum entropy, because we got our gas here, favors the products. Yes. Huh? Then I'm not going to give you a question like that. Okay? There will be no ambiguous questions. All right? Now, what if I were to throw in here a heat term? I meant to make that blue. Why is that not blue? No, blue. Ah, excellent. And I'm going to write blue instead of heat. That's awesome. Heat. Okay. Now, we need to also think about enthalpy. Which side does enthalpy favor? The right side. So is it minimum or maximum enthalpy that is minimum? Minimum enthalpy also favors products. So you have two forces of nature here. They're both pushing towards the products. Two forces of nature. They're both pushing towards products. What can you say about KEQ? Very large. Okay, if you have both entropy and enthalpy pushing towards products, it's going to be very large. Think about that candle burning, yes? That's an exothermic reaction. So heat is, enthalpy is saying, oh yeah, off you go, let's release some heat, let's get to a lower potential energy. What's more random, a candle or a bunch of water and carbon dioxide molecules? Water and carbon dioxide, so your KQ is going to be very large. So what can we say about the reaction? The reaction goes to completion. That was a little painful, but that's okay. Home. It's like we're doing a meditation or something. Completion. So if both forces are pushing towards the products, then you get these two things happening. Yes? We might just get through this. Let's do, we got two more. Yes? Yes, if you have enthalpy pushing one way and entropy pushing the other, you are going to establish an equilibrium. Yep. Yes. Yes. Oh my God. Look. So what Norman just said is that if we had, okay, let's just make it really, really simple. If I've got a solid over here, yes, and I've got a gas over here, then entropy favors the, oh, we did this one already, didn't we? No, never mind, I got it backwards. If this is a gas, that's what you were saying, right? If that's our gas and B is our solid, but our heat term is over here, yes? What we now have is we now have maximum entropy, saying reactants, and minimum enthalpy, favoring the products. And so you've got one thing pushing this way, and you got the other thing pushing that way, and that will give you an equilibrium. The system will form an equilibrium. No. There's a third set. Oh, here, let's do this. We've got CO2, which is a gas, plus H2O, which is a gas, in equilibrium with, or no, not in equilibrium with, is going to be our question mark over our arrow. Yes, we don't know which way it's going. So this one, oh, by the way, up here, come on back. There you go. What should we do with this arrow? That should be a one-way arrow. Yes? Going to completion. This one, though, candle, which is a solid, plus O2, which is a gas. Where's the heat term in this reaction? Heat. okay? Well, no, that would be backwards. Ah. So if the candle burns, that's the reverse reaction, yes? So my forwards reaction here, what does minimum enthalpy favor? Minimum enthalpy, yes. What about maximum entropy? Maximum entropy. And so what we've got is we've got two things pointing this way. So when we write an actual arrow for this thing, we're going to say this thing does not go in the forward direction. This reaction does not occur. So you can now do homework is study for your quiz. However, your quiz is on Thursday. It would behoove you, because your test is coming up, to also do a little bit of work on 2.3e and 2.4b. There we go. This will not be on the quiz, but it will be on your test. And we're going to be doing a lab, and we're